Hey everyone. In this video, I'm going to talk about the central limit theorem, sampling distributions, and uncertainty. And I want to review these concepts that we talked about in the past couple of weeks to answer some of the clarifying questions you had in our previous Q&A session. And the way we're going to talk about this, the idea of the central limit theorem and sampling distributions and how we use those to quantify uncertainty around our estimates, is a simple example. The simple example involves rolling a certain number of dice and then computing the average of those dice and using that sample average or that average as the average across for one sample, essentially. Okay. We'll look at this from a couple of different scenarios, varying the number of dice. So in that sense, the number of dice is equivalent to the sample size that we're going to think about, and we repeat this experiment a number of times, which is kind of the repeated data generating process, or the repeated sampling process that we can think about. Okay, so let's look at the first case. The first case involves a sample size of n equals 1. So we just have one die. We're going to roll that die and then compute the average, which is of course just the number that we rolled for that specific die. Okay, and we will do this 10,000 times. So that's 10,000 repeated samples that we're going to draw. Okay, you can think of that as the hypothetical repeated data generating process. So 10,000 iterations. We will have a sample size of 1, n is equal to 1. And what we're going to do is we will repeat the process, as I said, 10,000 times. So we will write a quick loop where we have first, we create an object here of a simple vector of length 10,000 that will save our average dice, the average number that we basically rolled. Okay, and then we run a simple loop where I iterates from 1 through 10,000. We roll the dice. Here in this context in R, in order to program this in R, what I do is I basically take a random draw from a uniform distribution, or n draws from a uniform distribution and it's a uniform distribution between 0.5 and 6.5. Okay, of course the uniform distribution describes a continuous random variable, but what we want is a category or an integer value. So what we're going to do is we're going to round this value, right? So so that means ultimately we simulate a random variable that takes either 1, 2, 3, 4, 5, or 6 as a value with equal probability. So that's equivalent to rolling a fair die. Okay. After rolling that die in our loop, we compute the average and save that average in our output vector average.dice I. Okay, and then the next thing we're going to do is we're going to look at the distribution of our averages, and so that is now what we think of as this hypothetical sampling distribution, right? One sample is just one die roll, and the sampling distribution is the distribution of averages across all our data generating processes, across all our dice rolls, essentially. Okay. Note here that the step of computing the average for these dice is essentially not necessary, because we only have one one die that we roll, essentially. But we're gonna, of course, change the sample size here in a second, and I just wanted to keep the code consistent, so that's why we have the mean here, even though we didn't really need to compute it with n equals 1. Okay, so this is all we're doing. We're rolling one dice. That one die roll is one sample, and we're looking at the sampling distribution as basically the number that we rolled across 10,000 iterations, across 10,000 data generating processes. Okay, And this is what this looks like. That's our histogram of our sampling distribution, which of course now shows 6 different outcomes from 1 through 6, and they all have approximately the same probability. Of course, because what we simulated here is a fair die. Okay. So this is the hypothetical sampling distribution with n equals 1. So where our sample size is just equal to 1. What we're going to do now is we will increase the sample size and examine how that affects our underlying sampling distribution. So in our next case, we increase our sample size to 2. Rather than just rolling 1 die, we're rolling 2 dice and computing the average of those 2 dice that we just rolled. Okay, the code is exactly the same. We just set n is equal to 2. We still have our output or return vector where we save our result for each iteration in the loop. We then run our loop again, 10,000 iterations, 10,000 repeated data repeated data generations. Then we now basically simulate 2 die rolls. Okay, same code here, and we then compute the average of those die rolls for each iteration, and then examine the histogram. And compared to the previous histogram where we had kind of equal probabilities for each of those dice, for each of those die rolls, we now have not uniformly distributed histogram, but rather we see, you know, around 3.5 is the most likely outcome. So we're already seeing now averaging 2 die rolls rather than just looking at 1 die roll, that this distribution already changes its shape in a certain way. Okay. We can further increase our sample size. Now we include 5 dice in our sample, so to speak, right? So we're rolling our dice. In each sample we're rolling 5 dice, and we're computing the average of those dice rolls, okay, across the 5 dice, and then we're repeating that process 10,000 times to have 10,000 sample averages of our repeated data generating process, and then we look at that histogram. And again, now already increasing this to 5, it's still clearly not normally distributed, but it approaches more and more the shape of a bell curve. Okay, if we go back to the first one, or the n equals 2, n equals 5 already kind of approaches this bell curve, right? What happens if we further increase the sample size? Well, it turns out the more we increase our sample size, the more this histogram across, or this distribution, the sampling distribution across repeated data generating processes approaches a normal distribution. So already when we talk about sample size being equal to 10 in the case of rolling n dice, we look at the sample average and see, or we look at the sample average and plot the histogram of sample averages across our 10,000 iterations. We see that this already looks pretty much in shape like a normal distribution, right? And so ultimately, that's the key insight from the central limit theorem, which is, if we look at these kind of sampling distributions, these distributions of sample averages across repeated data generating processes, we see that as we increase our sample size, in this case, just the number of dice that we roll in each sample when we compute the average number that we rolled, we see that the sampling distribution of x bar, so the average number, the average die roll, so to speak, approaches a normal distribution as our sample size increases, or as our sample size approaches infinity. Okay. And that's essentially the main key aspect the key insight from the central limit theorem, that as our sample size increases, of course this doesn't only hold for dice rolls, this holds for any other type of distribution, and the key is that, as we can see here, the original distribution, the die was a fair die, so that means essentially it's a uniform distribution with just integer values in the case of one particular die, right? So irrespective of the shape of the underlying random variable of x, which is clearly not normally distributed, if we look at the sample averages and the distribution of sample averages, then clearly it still approaches a normal distribution, right? So the key is, regardless of the shape of the underlying distribution of the individual random variable, like the die, the distribution of sample averages still approaches a normal distribution as long as the sample size is large enough. And that's why the central limit theorem is so incredibly powerful, because we don't have to care necessarily about what the underlying distribution of the individual random variable is, as long as we look at sample averages essentially, and want to kind of quantify or characterize the distribution of sample averages. Okay. And the other key point here that kind of connects this to this idea of the sampling distribution is that the variance of the sampling distribution is essentially what we use to quantify the uncertainty of our estimator x bar across repeated samples, right? So the key thing here is that, of course, in the context of our actual statistical analysis, when we base it on surveys, of course we can't run 10,000 surveys and look at the actual sampling distribution, right? We kind of have to think about the sampling distribution as a hypothetical construct, but nevertheless, if we were able to examine the sampling distribution over repeated samples, the variance in that sampling distribution, we would be able to kind of say how uncertain our estimates are, how much uncertainty there is around our estimates. Okay. So as I said, if we were able to collect repeated samples, for example with surveys, we could directly compute the variance of the sampling distribution to characterize the uncertainty around our estimates, right? And this helps us. Why does it help us characterize the uncertainty around our estimates? Well, it describes the uncertainty, or if we look at the standard deviation of the sampling distribution, this is the average deviation across repeated samples in our estimate, right? So we're interested in some estimate x bar, or maybe it's a regression coefficient, right? And ultimately, in order to think about or quantify the uncertainty around that estimate, we have to think about the uncertainty in the context of repeating the data generating process. How much deviation would there be across repeated realizations, either of our sampling procedure, of our survey sampling, and so on. Okay. Now, of course, the underlying problem is that we can do this when we simulate dice. We can do this kind of hypothetically, but in the real world, all we have is one sample. All we have is one survey with 1,000 respondents, and we have our average presidential approval or whatever, and we still want to quantify the uncertainty around that estimate, around that x bar, but we only have one sample. We only have that one specific realization of our data generating process, but we want to quantify how much, in this hypothetical world where we could repeat this 10,000 times, how much variation would there be around our 1 point estimate that we can compute for our one sample that we were able to collect, right? And this is where the central limit theorem ultimately tells us, luckily, that we can estimate the variance of the sampling distribution based on the variance in a single sample. Okay, so we can look at our variation in our individual sample, in the one sample that we have, right, the one time we rolled 10 dice, and look at the variation in that sample, and from that kind of estimate the variation that we are expected to observe across repeated sampling processes, across repeated data generating processes. Okay, and that's the key insight, that we can basically use the variation in one single sample to characterize the variation hypothetically in a repeated data generating process under repeated over repeated sampling in samples in that sampling distribution. Okay, and to kind of further illustrate how that works, I kind of expanded this example of basically simulating dice as rolling n dice as one sample, and simulating repeated sampling procedures. I extended that example a little bit. Okay, so let me go first through that code, and then I'm going to show you the results. Okay, so the code here is similar to the code that we looked at in the previous example, where we had just one specific scenario with one sample size that we then repeated 10,000 times. Now we're going to do this a little bit differently. We will go through different scenarios in terms of sample size. In addition to just 1, 2, 5, and 10, we'll go through 2 through 10, all or 9 different scenarios in terms of sample size. Okay, so in addition to the loop that we had previously for each iteration, we now have a loop here for n in 2 to 10, where we go through different sample sizes ranging from 2 dice to 10 dice. Okay, so we're basically filling up. While I showed you individual cases for specific sample sizes, we're now doing the same thing for any sample size between 2 and 10. Okay. Then we're going to compute the average sample size. The average dice value that we computed previously. That's the x bar, the estimate that we want to look at, and that's the quantity for which we also look at the sampling distribution. But we're also going to do something else. We will also compute the variance in that sample, right? So we have a loop here for each iteration, and from 1 through 10,000 again. So that's again 10,000 repeated data generating processes. We roll our n dice, same as before. We compute our average in our individual sample, same as before. And then we compute the variance in our sample. So for the dice values that we roll, we not only compute the mean, we compute the variance as well. Okay? And then we do that. After we do that, we save basically this result of the average, the sample average, the sample average, as well as the sample variance in individual objects for each sample size scenario, from 2, sample size 2, to 10, sample size equal to 10, so rolling 10 dice. Okay. And then what we're going to do is we're going to plot two things, or we're going to just create a simple scatter plot. On the x-axis, we will have the variance in our individual sample. So that's just the average within sample variance. Okay, so that's just, you can think of this as the variance, the average variance in a single sample. Okay, and then next on the x-axis, on the y-axis, we'll have the variance of the sampling distribution. The variance of the sampling distribution is just the variance of the as well as it says, the variance of the distribution over repeated 10,000 data generating processes, right? So we have 10,000 realizations, we roll n dice 10,000 times, we compute the average, and then compute the variance across those 10,000 realizations. So that's the variance that we ultimately want to estimate. That's the variance of the sampling distribution based on our individual sample, okay? And so we're just going to look at how the sample variance is related to the variance of the sampling distribution for varying sample sizes. Okay, that's what we're doing here based on this simulation. Okay, and if we plot this, this is the result. And actually that doesn't look very promising, right? We have the numbers here are the individual sample sizes. On the x-axis, as I mentioned, is the variance, the average variance in a single sample. And on the y-axis, we have the variance of the sampling distribution for that specific sample size. Okay, so that's the variance of those of this distribution for n equals 10, the variance of this distribution for n equals 5, variance of this distribution for n equals 2. Okay, and what we see is there's hardly any relationship, and really it's you know, there's just, you know, these dots are basically anywhere. We have very high variance in the single sample for n equals 2, high variance in the sampling distribution, but it's clearly not a clear, you know, linear relationship or anything like that, right? So does that mean the central limit theorem is wrong and we cannot estimate the variance of the sampling distribution based on the variance in a single sample? Of course not, right? Of course that's not the case, but it's not so simple. We can't just say, okay, the variance in the in a single sample is equal to, or is, you know, directly linearly related to the variance of the sampling distribution. Why not? Well, we missed one important part, and that important part that we missed is that the variance, the estimator for the variance of the sampling distribution based on the variance in the single sample is the variance of the underlying random variable divided by the sample size, right? So in this case here, I'm going to change this plot, and rather than looking at the variance in the individual sample, I will plot the variance in an individual sample divided by the respective sample size down here. And again, that's going to be on the x-axis, and on the y-axis we will look at the variance in the sampling distribution. Okay, so now we look at the relationship between the variance in a single sample divided by the sample size, and on the other hand, the variance of the underlying sample or the resulting sampling distribution over repeated data generating processes. And if we do that, the results all of a sudden looks like this. We have a clear, you know, linear correspondence between the variance in a single sample, which is on the x-axis, and the variance in the sampling distribution for varying sample sizes, right? So as soon as we divide the variance in a single sample by the sample size, that quantity is equal to the variance in the sampling distribution. So luckily, we don't have to repeat our sampling procedure 10,000 times to know how the sampling distribution would look like. As long as the central limit theorem holds, we know that we can estimate the variance in that sampling distribution, in that hypothetically repeated data generating process, based on the variance in a single sample. And that's by dividing the variance in that single sample by the sample size. Okay, and that's pretty cool. That's a pretty cool result. Okay, so to summarize, and this is kind of bringing back some of the slides that you saw already, but now kind of with this illustration based on this simple example of rolling dice, we can kind of go through the summary of the central limit theorem again. The key point of the central limit theorem is that suppose we obtain a random sample of n IID observations, x1, x2, xn. And in our case, we could think of these as rolling dice, rolling n dice, okay? From a pure probability distribution with mean expectation of x, and variance of x. Okay, so it has a defined mean and defined variance, right? Then we can denote the sample average by xn bar. Okay, that's the average i's that we, or the average number that we rolled on that die, on those n dice. Okay, and that's just all the x's summed and divided by n. That's just the sample average. Then the central limit theorem states when n is large, we can say that xn bar, so the sampling distribution, the distribution of xn bars over repeated sampling or over repeated data generating processes, so to speak, follows a normal distribution with a mean that is equal to the expectation of x, and a standard deviation, a variance that is equal to the variance of x divided by n, right? This is the key aspect where the variance in the sampling distribution can be estimated as the variance in the original random variable divided by the sample size. Okay, we can of course not only kind of show this in the example of our simulations, we can show this analytically, that the average or the average of that distribution is the expectation of x, and the variance is the variance of x divided by n. And I showed you this in previous videos, but just to go through this quickly again, if we take the expectation of our xn bar, we can just plug in our the underlying equation for the sample average, which is 1 over n times the sum from I equals 1 through n of xi's. And of course, these are, we can pull the 1 over n in front of the expectation, and the sum, the expectation of a sum is the sum of expectations, so we can pull out the sum as well. So that's 1 over n times the sum of I equals 1 through n of the expectation of xi. Now xi is an IID random variable, so it's identically and independent and identically distributed, so they all xi's have the same expectation, namely the expectation of x, so the sum or summing up n expectations is just n times the expectation, and then we have 1 over n times the expectation. That just simplifies to the expectation of x, and that's why we have the expectation of x up here. Now moving on to the variance of x bar, again we can just plug in our equation for the sample average. That's 1 over n sum of I equals 1 through n of xi's. And again, we can pull out the 1 over n as well as the sum, but keep in mind that if you pull out a constant, a variance of a times x is equal to a squared times variance of x. So this turns into 1 over n squared sum of I equals 1 through n of variances of xi. Again, this variance of xi is just the variance of x, right? That's what we have here. Summed n variances that are independent summed together, that's just the sum of the variances, so that's n times the variance of x. And of course 1 over n squared times n times the variance of x simplifies to 1 over n variance of x. So that's where this variance is coming from. Okay. And of course the standard error, which we usually use as kind of the measure of variation in the standard in the sampling distribution, is just the square root of the variance of the sampling distribution. Okay, so the standard error is equal to the square root of the variance of x bar n, which is just the variance of the square root of the variance of x divided by n, or written differently, the standard deviation of x divided by the square root of n. Okay, and that's how we compute the standard error based on the central limit theorem. And again, what the standard error tells us is the average deviation in our estimator across repeated data generating processes, across repeated sampling. If we were to repeat our sampling procedure, the standard error tells us how much our estimator or how much our estimate would on average vary across repeated data generating processes. And that helps us kind of quantify the uncertainty, or that is how we quantify the uncertainty around our estimate based on this idea of repeated sampling procedures. And based on the central limit theorem, even though we only have one sample, we can use the variance in that individual sample, if we have a large enough n, to characterize the variance and standard deviation in that sampling distribution. And the standard deviation of the sampling distribution, that's what we call the standard error. And I think that's all for the central limit theorem and sampling distributions. I hope this clarifies some of the questions that you had in the last Q&A. If you do have more questions, feel free to ask in the next Q&A, and I'm happy to go through these examples in more detail. In the next video, I'm going to talk about hypothesis testing.